So now what we want to do is we want to see what would happen if we had a resistor, inductor, and a capacitor in one circuit. In this case, I'm going to make a series RLC circuit. Okay, and so we have a voltage source. We're going to say the voltage is V0 sine omega t. Okay, so now what does this circuit do? So what does this circuit do? And so to figure out what this circuit does, then we have to remember how voltage and resistance all play out in here. Now, to do that, we are going to introduce another concept called a scalar or a phasor. So a phasor. So we can imagine here that in Physics 1, we talked a little bit about how harmonic motion is very similar to circular motion. So if you had, for example, some x right there, and you just look at the x component, as this went around with some angular velocity there, the x component there, if that were x naught, would be equal to x naught cosine omega t. Well, that's exactly what you get if you do the x component of circular motion, but that's also what you get if you had something moving in harmonic motion. The force, the centripetal force right here, the component of the centripetal force turns out to also match what you get for the force of the harmonic oscillator. The velocity is the rate of change of this, so if I take a derivative of that, I get velocity. That again matches the harmonic oscillator. So for the harmonic oscillator, we could imagine just the x component of circular motion matching. We are going to do the same thing here with electric circuits. We're going to say that we've got some voltage right there. And that voltage, we're going to say this is the real axis and then the imaginary axis. So the real axis, that's going to be the y component of that. So that's going to be equal to, we're going to say this is V naught, V equals V naught sine omega t. Okay, so that's going to be our scalar for voltage. Now, for current, in the series circuit, if voltage is like that, the current in the resistor, IR, is going to be like that. So IR equals V naught, the voltage on the resistor divided by R. Okay, but we also know that for a capacitor or an inductor, then we have another thing going on, and that is the current in the capacitor or the current in the inductor are out of phase. Okay, so the current in the inductor is lagging behind the voltage. The current in the resistor is leading the voltage. So how do we play all that into this? Well, if we were to draw scalars or other phasors for that, we would say we got voltage on the inductor and the current lags behind. For a capacitor, we have the voltage on the capacitor and the current leads, okay, by pi over 2. Okay, now, for our circuit right here, for our circuit where it's a series circuit, then you have the same current in everything. So that means that we can imagine just one current, I. The voltage on the resistor is in phase with that. But, Eli, the voltage on the inductor leads. And the voltage in the capacitor, ICE, lags. So if we add these two vectors together, we have VL minus VC. And so we could then draw that. Total current, voltage in the resistor, and that's going to be VL minus VC. Well, we got these two vectors, so Pythagorean theorem, the total right there, V, is going to be the square root of VR squared plus VL minus VC squared. Well, if we plug it in, that voltage equals square root of I squared R squared plus, I XL minus I XC squared. Okay, we can factor out V equals I times square root of R squared plus XL minus XC squared. Okay, well, V equals IR, well, obviously, this thing right here is not R. This is something else. We're going to call that Z for impedance. So V equals IZ. So that's our impedance. And so that means that Z is going to be the square root of R squared plus XL minus XC squared. We could plug that in. R squared plus omega L minus 1 over omega C squared. Or we can go one more step if you'd like, and that is R squared plus 2 pi FL minus 1 over 2 pi FC squared. So that is the impedance of a series RLC circuit. Notice that when XL equals XC, that's your resonance. So if XL equals XC, then the impedance, which is square root of R squared plus XL minus XC squared, is just going to be equal to R. So that's going to be your minimum impedance, is at that resonant frequency. So the resonant frequency occurs when XL equals XC. So XL equals XC, this is our condition of resonance. And so that would be omega L. So omega L equals 1 over omega C, or omega squared equals 1 over LC. Omega equals 1 over square root of LC. Remember that omega is equal to 2 pi F. And so the resonant frequency is going to be 1 over 2 pi square root LC. Okay, and so y'all did that in lab. So I don't really need to belabor that because we did this in lab. You had a whole lab on AC circuits. So this is the mathematics of how that happens. Okay, so this is for a... What do you think a parallel RLC circuit would be? So we have a resistor, we have an inductor, we have a capacitor. So you think about it and we say, well, in that case, the voltage is the same on everything. So that means that IR is right there. So that means that Eli, IL, is lagging, or for the capacitor, IC is leading. So the current leads in the capacitor. And so we would say here that we could then say that we've got the voltage, same with everything. We have IR, here we have IL minus IC, okay? And so the total I is going to be the square root of IR squared plus IL minus IC squared. Well, if V equals IZ, then that means that I equals V over Z. Okay, so V over Z equals square root of V over R squared plus V over XL minus V over XC squared. So we divide things out. 1 over Z equals the square root of 1 over R squared plus 1 over XL minus 1 over XC squared. And so that would give you an expression for how you would find the impedance for a parallel system. Notice also that as we did this, that for the series circuit, that once again we had I here, but the total voltage was right there. So there's a difference in there. There's a phase angle. So the phase angle would be, well, this right here is going to be V, that right there, so is going to be, so the tangent of the phase angle is going to be VL minus VC divided by VR, which was that right there. And so we can look at that and say, therefore, the tangent of the phase angle is going to be VL equals IXL, and then minus VC, which is IXC, divided by IR. The I's cancel, and so the tangent of the phase angle is going to be XL minus XC over R. And so this gives us our measure, the phase angle. This is the angle, the phase angle, that determines how much the current and voltage are separated. In other words, this measures how much the voltage is leading. So if we have a positive phase angle, that means the voltage leads. Negative phase angle means the current leads. Phase angle of 0 means the current and voltage are in phase. And so again, this is some of the stuff that you had noticed when you were doing lab.